Okay, hello everybody. We're going to really quickly discuss basically the stresses and strains that come about when you have beams and trusses. So we're going to quickly recollect what stress and strain actually means, and then we'll talk about what static equilibrium is, and then we'll kind of do the stress and beams with a simple example, and then look at stress and truss with another simple example as well. Really quickly, if you think about what a force is, it's a physical interaction. So essentially, if you want to like pull or push something, if you haven't constrained it, it's going to kind of like run away. So if a force is a physical entity, if unopposed, it actually causes acceleration. So in dynamics, what we're typically trying to do is we are interested in the magnitude of the acceleration or the change in the direction of motion. So what we'll do is we'll basically actually have the acceleration as a value and then try to calculate the actual path of the object. In statics, the object is typically trying to resist the force, so it's not actually trying to move. You have either like fixed it at one end or done something else, basically apply an equal and opposite force to basically make sure that the object doesn't move. So that's the reason it's called statics. So essentially the force is transferred through the object. So that's the important thing. So generally when you apply a tensile force, it's trying to pull the molecules or the atoms of the object apart. And you can have a compressive force, that tries to squish it down to a smaller value. Force tries to break the object essentially. So the strength essentially is how much force you can apply before the object actually fails. Empirically, we know that if the cross section is larger, you can apply a larger amount of force before the structure actually fails. So we are interested in force per unit area, which is known as the stress. When you apply a tensile force, which is basically like pulling on the object, so essentially you kind of like pull on the object, then we apply the stress that's developed is known as a tensile force. So that basically makes it thinner and then tries to fall apart. When it tries to squish the object down, essentially kind of like compress it down, what we are applying is known as a compressive force, and it results in a compressive strain. The stress has the same unit as pressure, and it's Newton per meter squared or Pascal. Anytime you apply a stress on an object, it kind of deflects. So essentially if I take this pen, actually I don't want to break this. If you take any object, kind of like if you apply a force, essentially this piece of paper, it kind of like deflects along the direction of the force. The longer the object is, the more it deflects or deforms. So we are interested in kind of the relative strain or relative change in length, which is known as a strain. So the strain is defined as the change in length by the original length, and strain being a ratio doesn't have any units. Tensile strain basically corresponds to an expansion, basically things becoming larger. Negative strain or a compressive strain makes the object smaller. For elastic material, the strain is usually proportional to the stress. So it's given by this equation, sigma here, which is the stress, is equal to E times epsilon, where E is the Young's modulus or the modulus of elasticity. When we have static equilibrium, we use certain symbols to kind of convey the idea of how the object is actually restricted. These are known as constraints. So typically when you have kind of this shape here, this constrains the object both in the X and the Y direction and the direction of motion. So if I basically have an object like this, typically it will be a beam like this. That basically means that the beam cannot move in either direction. So it's kind of prevented from moving like this, and then it cannot rotate either. This constraint basically just makes sure that the object cannot move in the X direction. So essentially it cannot move like this, or it cannot move in the Y direction. And then this corresponds to kind of like a pivot point. And then this having wheels, this can actually move in the vertical direction. So it's free, or it's constrained only in the X direction. Generally what we do is since we were interested in finding the forces at these constraints, we typically replace these forces with we replace these constraints with corresponding forces. Essentially, if the object cannot move in the X direction, that basically means that the support needs to apply x direction force to prevent it from moving along the x direction. So essentially based on the number of constraints that we have, so if you have an x, y and rotation constraint, so you apply two fx and fy, two forces, and a moment to prevent the rotation. So essentially if you have this kind of a constraint, you replace it by the x and y force and a moment force, a moment. This one gets replaced by an fx and an fy, and this one gets replaced by an fx. When we are looking at beams, typically we look at what's known as an Euler beam. It has a linear elasticity and it's valid for small deflection. Essentially if the deflection becomes very large, the location of the force changes a lot, and then there is kind of like secondary effects. The length is significantly larger than the thickness. Again, this prevents or we can kind of like ignore secondary effects. The relation between the deflection W, the distributed force Q, shear force V and M is given by these three equations. It's basically a differential second order equation, and the stress at any location is given by My by I. Typically we are not interested in these first two equations unless you're doing statically indeterminate calculation. So we're mainly interested only in this equation over here. So we basically would use this equation and this equation over here. So the first equation here can be used to calculate the total deflection, and then this one will be able to actually calculate the strain in the object. So the way it works is typically you take a beam, calculate the bending moment, which is denoted by M at one particular section. Once you have the bending moment, you can actually use this particular formula over here. Sigma is m h/2 by I, where I is the area moment of inertia given by 1 by 12b h cube for a rectangular beam. So this is an example. So we're going to really quickly calculate a beam here, which is kind of fixed at this end over here. So this is a fixed support, and then you apply vertically force down of 10 newtons, and the beam is 100 centimeters, so this length is going to given to be 1 meter or 100 centimeters, and then the cross section is 10 millimeters by 10 millimeters or 0.01 meters. And so we're going to calculate this particular value. So now would be a good time for you to pause the video and then try to do the calculation yourself. So here is the solution. The first thing you do is take the beam and then create the free body diagram. So what do we mean by free body diagram? So essentially we want to get rid of this support over here. How do we get rid of the support? We would basically apply a vertical force because it prevents the vertical motion, and then we should actually ideally also apply a horizontal force. But since there is no other horizontal force, this force will actually come out to be 0, and then we apply a moment at the support over here. Essentially, we can potentially cut the beam at any particular section, so this length is actually variable, so you don't have to just cut it at this point. And so if you have to take the equilibrium at this particular beam at a length L, so I'm applying a 10 Newton force, the bending moment that I'll need to apply over here, this is going to be 10 times L. So as L becomes larger, my moment is going to be larger, and the maximum moment basically occurs at this particular support over here. So basically the maximum bending moment, M max if you want to call it, or just M, is basically going to be 10 times 1 meter or 10 Newton meter. So now that we have the maximum bending moment, we can actually calculate the sigma, which is basically sigma is going to be this M, and then we need to multiply by the half the height, and then we need to divide by the I, which is the area moment of inertia. So we need to actually calculate this value of I. So we'll keep this. So how do we calculate I? So I is the moment of inertia, which basically is 1 over 12. And then we get 0.01, and then because B and H are the same value, this becomes to the 4. And then when we calculate this basically becomes 8.3. And then so times, so you get 10 to the minus 2 over here, and then this is basically 10 to the minus 8. So this becomes 10 to the minus 10. Then we can actually calculate the sigma max, which is basically the n, which is basically m is 10 times 1. And then we're going to multiply this by h over 2. And then we divide this by this I value that we get here. So 8.3 times 10 to the 10 minus 10. So once we do this, we'll actually find this to be 60 megapascal. Right. So this is the calculation. If you're interested, what we can actually do is also calculate the deflection of the beam. So for that, the formula that we need to use is so this basically becomes F L cube divided by 3 EI. As before, if we substitute all these values, so this comes to about 2 times 10 to the minus 5 meters. So basically this beam starting like this would kind of go here, and then this is the deflection that we have actually calculated. So the next thing we're going to look at now is truss analysis. So first we're going to look at some of the assumptions that go into the truss analysis itself. So essentially a truss kind of looks like this. And then the first assumption we make is that the joints here, like so if I have another link over here. So we basically assume this is actually a pin joint. So what is meant by a pin joint is that this arc link can freely rotate about this particular joint. The next thing we assume is that all the external forces actually act at the joint, and then we assume that the link does not carry any moment and that all the internal forces are purely axial, and then what we do is we also neglect the weight. So notice that if we say the link does not carry any moment, that basically means that all the internal forces would become purely axial. So notice that if all the joints are pin joints, then the link cannot actually carry moment. Basically, because if I put a moment over here, what is going to happen is that this link is actually going to just rotate freely like this. So this here, basically saying all joints are pin joints, and then all external forces act at the joint are the primary references. And then the rest of it kind of follows. Basically, we neglect weight as kind of a normal assumption, and then the rest of it follows suit. The sign convention that we use is when we say we have a tensile force, we basically call it to be a positive force, which is basically if I have a link like so, and then I'm pulling on it. Actually, you can say I'm pulling on it. That is a positive or a tensile force. And then if I'm trying to squish the link down, that is a compressive, and the sign convention for it is negative. We are typically interested in doing a free body diagram. Essentially what we do is we want to separate the pin joint from the link. So in doing that, what we need to do is we need to apply a pulling or a tensile force. So essentially the link, basically the force goes towards the center of the link, and on the link the force is applied towards the joint. So notice that if I kind of bring this over here, these two are known what is known as internal forces. So this force would be equal to this force. They'll basically cancel each other out. There wouldn't be any force when I assembled it together. So there is not a net external force. So this is important. Make sure that the force are equal and opposite. So this, because you're assuming tension, this needs to be a pulling force. So basically in this direction, and then that basically results in a pulling force on the link as well. So now we're going to do a simple truss example. We're going to assume that this link is 1 meter, and then the cross section is basically assumed to be 1 centimeter squared. And then what we're trying to do is calculate the maximum stress. So we basically have two links over here. So either one of those can potentially have a maximum stress. So essentially we need to figure out what the maximum force is. And then because all the forces are axial, so basically if I have a sigma axial and I know the load internal tension, if I divide this by the area of each of the link, that will give me the axial strain. So at this point, it will be a good time to take or pause this video and then try to solve this yourself. All right. So first thing we do is kind of number these links, number these joints, excuse me. We can kind of number it any which way you want, but what I typically do is kind of start at this point, number it counterclockwise direction. So now we're going to try to calculate the equilibrium, excuse me. So what I'm going to do now is kind of calculate the equilibrium. So essentially the first thing I do is kind of get rid of the supports. So this is basically going to restrict it from moving along the X and the Y direction. Same goes here. So basically then I would apply two forces here. Same thing over here. Apply one force like so, another force going up. So we can call this, we'll call this Fy1, and then this is basically Fy3, and then this is going to be Fx1 and so on. The next thing we're going to do is kind of separate these out and then kind of just look around this link alone. So if we do this, just like here for this particular node, what we need to do is apply here, note recall from the previous exercise. I'm going to apply a force which is tensile, which is pulling on this link. So this is going to be tensile pulling on this link as well. The force here needs to be pulling, so basically along this direction, and then over here basically along this direction, and then same way pulling over here. So both of these would have a value of T, and then since it's between the link, this is number 2 by the way, between 2 and 3, we're going to call it T23, and then this force here is going to be called T12. So we kind of pick only the link 2 and then try to apply static equilibrium. For that, we need to resolve these forces along the X and the Y direction. Basically, I'm going to assume the horizontal is the X and the vertical is Y. So if you do the X equilibrium, I have to resolve these forces, and then T12 is pointing along the negative X. So I'm going to say negative T12, and then I'm going to resolve this force along the X direction, and so that becomes plus, and then once I resolve this becomes negative T23, and then this angle is theta, so this basically becomes cosine, and then theta, and then if I want to do the Y, and then this would be equal to 0 because there's no other force in the X direction. Same thing with the Y. So Y, there is a negative force here, 10 newtons going down, so this is going to be minus 10. And then I need to resolve this force along the vertical direction. So because it's going to go up, so this basically becomes plus, and then we have t23, and then this is going to be sine, and then this is equal to 0. So this equation here only involves t23, so we can basically use this to calculate the value of t23, and then sine theta, theta being 45 degrees, sine theta is 1 over root 2. So this basically gives me t23 is 10 divided by root 2, excuse me, 10 divided by 1 over root 2. This basically gives me 14.14. T12 would be minus T23 divided by that would be cos theta so this basically becomes minus 10 newtons. So what this negative sign basically means is that the force I initially assumed basically is pulling on this, but the actual force needs to be pushing down with a value of 10 newtons. But we still leave the force along this direction and then just assume that it's a negative, which basically implies it's a compressive force. So this is the values we calculated. What is going to happen next is if I want to calculate the strain, I need to divide each of this by the cross-section area. So if you recollect, the cross-section area was basically is the same for both of these, and then this is basically for a rectangle it's going to be base times height. Since base and the height was basically 0.1, so this basically becomes 0.1 meter squared. So sigma 1,2 is going to be 10, the unit was newtons, that divided by this area is going to give me 0.1 megapascal. So this is 10 to the minus 4 minus 5, and then I get one more, 10 to the minus 6. Megapascal is 10 to the minus 6, excuse me, 10 to the 6 Pascal. Similarly, we can calculate sigma 23, which is going to be same thing, 1.414 divided by this area over here, so that gives me 0.1414 megapascal. So once I have this, I can actually calculate the deflection. The deflection, since I know the strain over here, the stress over here, the strain of 1,2 would be equal to sigma 1,2 divided by the Young's modulus. And then similarly, epsilon 2,3 would be sigma 2,3 divided by the Young's modulus. So let's actually look at just sigma 2,3. So if you look at this, this will give me the Young's modulus. If you assume it's a steel, so we basically take this value divided by 200 gigapascal, and then to get the length, delta L, we need to multiply this epsilon 2,3 divided by the length. So in this case L23, so you need to go back. The length is basically going to be the diagonal, which is going to be root 2 times. And so we can actually substitute these values and then calculate the length. We would find that the change in length is delta 2,3. we actually find this to be 2.41 times 10 to the minus 11 meters. So basically you have this link like this. This is basically going to be 1.414. So this is 2. So this basically just becomes a teeny bit longer along this direction. So we wanted to calculate basically the x and the y deflection. So I kind of know that it's become longer by 10 to the minus 11. So I'm going to resolve it along the vertical and the horizontal. And then that will give me an idea of the magnitude of the actual deflection. But nonetheless, the magnitude of the deflection along the force would be kind of roughly in the same order of magnitude. So this basically concludes our brief discussion on stress and strain in trusses and beams.